let's control, we can tune S-wave interactions in the lab with something called Feshbach resonances, and as recently we can also tune P-wave interactions. What it means is that we can use cold atoms in the lab to create unitary Fermi gases and emulate neutrons and get conclusions about neutrons and neutron matter without ever touching neutrons. So today we'll be talking a little bit about cold atoms, but always from that perspective, from the perspective of what can we learn from cold atoms that will be useful for nuclear physics and nuclear theory. So as promised, I'll be talking a lot about neutrons and pairing of neutrons. So what I mean by pairing of neutrons, so neutrons are abundant in neutron stars, as I said. So in the inner crust of a neutron star, which is the region between 10 to 12 kilometers from the center of the star, around 10 to 12 kilometers from the center of the star, we find a fluid of neutrons. And at this density, we know from scattering experiments that the nuclear interaction is attracted mainly through the S-wave channel. That makes neutrons create pairs of opposite spin, and that turns neutron matter of the inner crust into a superfluid. Now, the existence of the which we call the S-wave superfluid, which comes from the S-wave interaction. So the existence of an S-wave superfluid in the inner crust is well established. As a phenomenon, it's very well established. It has been connected. It has various signatures in the cooling of the stars. It's been connected to regularities in the periods of pulsars, and so on. However, an exact description of those superfluids for all relevant densities has been elusive. We have an exact description for very, very low densities, but an exact description for all relevant densities of the inner crust has been elusive because of the very complicated nature of the nuclear interaction and how it changes, how the relevant channels change with density. So the first part of this talk, I will show you exactly how to prescribe an exact description of these superfluids for all relevant densities of neutron stars, at least for the ground state of those superfluids. So to solve for the ground state of a superfluid is basically it's one of the main parts of the quantum many-wide problem. And in nuclear theory, we have essentially two ways of going about solving for the ground state of a system. So we have phenomenology, which is we make some assumptions about the system we're looking into that gives rise to a phenomenological model, which is easier to implement, convenient to work with, but usually these assumptions come as uncontrolled approximations in the sense that it's hard and oftentimes impossible to quantify the errors that we're introducing in the calculation by making these assumptions. On the other hand, we have ab initio first principles. We solve the main Bell Schrodinger's equation with no extra assumptions, no controlled approximations, and we get essentially exact results. The shortcomings in any of these methods are that they tend to be very computationally expensive. So, for example, one of the best ab initio methods we have today, which is the one that I'm talking about, also quantum Carlo, can only do up to a few hundreds of particles. And to describe infinite matter with these, there is an extrapolation that needs to be made to the thermodynamic limit, which is oftentimes non-trivial. Of course, I should parenthesis here that there's been a lot of this discussion lately of what it means to do ab initio nuclear theory. And I should say that, of course, a lot of it depends on how you treat the nuclear interaction. If the nuclear interaction that we choose is not connected to the underlying symmetries in some systematic way, of course, any claim of ab initio results should be diluted. But I close this parenthesis. Ryan actually will talk more about that later. So what we do is that we make those two work together. We use a phenomenological model to get a sense of the effects, in this case, superfluid in neutron stars. And then we use that knowledge to guide expensive ab initio calculations, which will give us essentially exact results, which we can use to constrain phenomenology and inform it about the approximations that is made. So how do we apply that to a superfluid neutrons? We'll start with a phenomenological description. A very successful phenomenological model for superfluidity is the BCS theory. The BCS theory was introduced in the 50s to describe pairing of electrons in superconductors, and it describes the ground state of a superfluid as a condensation of pairs. You see, its term in this product either creates a pair or nothing. So its momentum state is either empty or it contains a pair. And those U and V coefficients, you can think of them as variational parameters that are optimized to minimize the pairing Hamiltonian, which is a Hamiltonian where we ignore all normal state interactions and we only consider the interaction that is responsible for the creation of the pairs. In this case, as already said, that's the S wave part of the nuclear interaction. Now you can see already why this is a phenomenological model. There's all kinds of assumptions for the form of the ground state, which we have no a priori reason to believe that it's quantitatively correct. For example, it turns out that the BCS wave function describes the superfluid of free quasiparticles. So any process that depends on scattering of quasiparticles is already excluded from this. However, this is the simplest way to include pairing correlations. So it should still give us a qualitative understanding of the pairing effects in neutrons. So, and indeed, we can calculate, for example, the order parameter of the superfluid, which is the pairing gap, and we can, which is essentially we call the pairing gap is the binding energy of those pairs, which I put here with on the y-axis, and indeed on the x-axis is the fermi momentum, which is essentially just a proxy for the density. So you can imagine the x-axis as going deeper into the star. We see that this is nothing new. We know that BCS predicts a sizable gap for neutrons in neutron stars. However, again, we have no a priori reason to believe that this is quantitatively correct. There's all kinds of assumptions that in a strongly interacting system like neutrons, they shouldn't necessarily be true. However, this is still a good qualitative description of what's going on, and we can use that to guide a more precise ab initio calculation. How do we perform this more precise ab initio calculation? First, we forget about the pairing Hamiltonian. We have to do a full nuclear Hamiltonian with a full nuclear interaction. The nuclear interaction, we all know it's a very complicated interaction. It takes 2-body, 3-body terms, and so on. We use the argon ABA interaction to model the 2-body terms, and the Urbana 9 interaction for the 3-body terms that contains a 2-binary exchange term and some reminder that just sums up all neglected terms. Now the question is, how do we solve the many-body equation with a complicated Hamiltonian like this? Our method of choice is diffusion with Carlo. I should. You probably cannot see my title, but there. All right. So our method of choice is diffusion with Carlo, which is based on the fact that the strength this equation in imaginary time turns into diffusion equation. What that means is that if I start with a Chiral wave function and evolve in imaginary time, all the components of the wave function that correspond to excited states of my Hamiltonian will die off exponentially. And eventually I will be able to project on my ground state and my ground state energy. We use the auxiliary field diffusion with Carlo, which operates on the same principle, just can handle more complicated interactions, spin dependence, and so on. Now there's a caveat to this, which is that my Chiral wave function is all very nice, but my Chiral wave function should be physics aware. In other words, it shouldn't be orthogonal to my ground state. Otherwise, this C0 coefficient will be 0, and I will never be able to project on my ground state. What does that mean in simple terms? It means that my Chiral wave function should be a good qualitative description of my system. It should know about the physics that I'm looking for. This is one way that our phenomenology guides our diffusion Monte Carlo results. We know that the BCS wave function is a good approximation, a good qualitative description of the system. So we use it as a Chiral wave function, and we make diffusion Monte Carlo project out of it the ground state. So that's exactly the Chiral wave function that we use. Okay. This is like the Chiral wave function that we use, where this first term here is just a symmetric part, which is there to reduce the variance of the calculation. These are all stochastic calculations, so the lower the variance, the more efficient the calculation, but the main physics are in the anti-symmetric part, which is this, which is a Pfaffian, which is essentially just a coordinate space representation of the BCS wave function. Indeed, the pair wave functions are of the BCS type, and we actually take things one step further. Instead of using those U and V parameters that have been optimized to minimize the pairing Hamiltonian, we re-optimize them to minimize the energy of the full Hamiltonian, those C alpha parameters. Now, this is not the only way that our phenomenology guides our ab initio results. For example, we have a travel wave function and we have a way of solving the Schrödinger's equation. That means that we get exact results for a finite number of neutrons, the ground state energy for a finite number of neutrons. How do we calculate from that pairing gap, which is the order parameter of the superfluid? And secondly, how do we extrapolate from that to the thermodynamic limit, from 66, from 70, 100 neutrons to an extensive system? That's all questions that our phenomenology can answer. So we first, there's the first question, we demonstrated that the familiar odd-even staggering that we know from experimental nuclear physics is a modally independent extractor of the pairing gap. Again, with a phenomenological study, and we also prescribed an extrapolation scheme from finite systems of 66, 67, 90, 100 neutrons to the thermodynamic limit. Both of those turn out to be not very trivial to do, exactly because they talk about finite systems, and the BCS theory is formulated in a grand quantum ensemble, so there needs to be a symmetry restoration and so on. There's a lot of technical details, so I'll just refer you to the two applications that we worked on those. We showed these things on, and I'll just move to the final results, where we get, using all of these that I just showed you, we get essentially exact results for the pairing gap of neutrons for all relevant densities in the inner crust. We see that the BCS, the mean field description was qualitatively correct, but there's around a factor of 2 suppression from the mean field results. Again, I'm not sure that those are essentially exact results up to their error bars, right? So all of this up to this point was about S-wave superfluidity. So that is pairing of neutrons in state of opposite spin. What types of pairing can we have? We can have what we call P-wave superfluidity, which is pairing, for example, neutrons between same spin particles, between same spin particles. An interesting question arises as well, which is, can we have S and P wave superfluidity? Can we have a superfluid with particles that paired in pairs of opposite spin and also in pairs of same spin? So that's a type of question that we need to answer. And before looking into it in the sense of nuclear matter, we visit the cold atoms that I mentioned in the beginning. So why in cold atoms? Why do you want to answer this first in cold atoms? Well, first, again, we know that we can control S-wave and P-wave interactions and their competition in cold atoms. And when we're looking for such a coexistence of the two channels, we predict that to be important, to be able to control the two. And we can also control spin polarization, which will also turn out to be important in a second. So we're working on this with some local people here, with Dean Lee and Gabriel Given and Kelvin Hicks. I think Kelvin's not here, I think he's online. And basically, the answer that the question that we're trying to answer is, can we prescribe a simple interaction between up-down particles, up and down particles, which we can tune in the lab and with cold atoms in the lab, and we can get some results that are relevant to nuclear physics, and specifically about S-wave and P-wave pair, S and P-wave pair. So I approach this from the BCS side, from the mean field side. I do the simplest thing possible. Again, we start with a pairing interaction, with a pairing Hamiltonian. We neglect all normal state interactions. We only consider the interactions that are responsible for the creation of the pairs. That is, the color coding from this point on is blue for S-wave, red for P-wave. So an S-wave interaction between opposite spin pairs, and a P-wave interaction between same spin pairs. We tune our S-wave interaction to unitarity because we know that the S-wave interaction in neutrons, for example, is very close to unitarity, and then we vary our P-wave strength to see if we can find a coexistence of S and P-wave superfluidity. We also generalize the BCS wave function to include both types of pairing, both same spin and opposite spin pairing. And what we find is that these states exist, but they're not in the ground state of a unitary Fermi gas. What do I mean by that? We do find states where particles of opposite spin paired. So this is the Guelph function. You can think of it as the binding energy of a pair with momentum k. So we find some binding energy between pairs of up-down spin. We also find some binding energy between pairs of up and down spin. but it turns out that the fluid can always lower its energy if it closes one of the two channels. That is kind of demonstrated in the plot that we saw on the right. On the x-axis, I have the autoparameter of the S-wave the S-wave pairing. On the y-axis, I have the p-wave autoparameter, and the black points are the pairing gap, the binding energy of the whole superfluid. And we see that actually closing the p-wave pairing gap increases the binding energy of those pairs. They tend to actually close one of the two channels. So what does that lead us? That seems to imply that at the ground state of a unitary Fermi gas, the ground state of the unitary Fermi gas, at least on the main field level, there is no S and P wave pairing. So where do we go from there? One thing that is interesting to look at is that we know that there's been predicted, there's S and P wave pairing predicted with more exotic interactions, more exotic settings. So it will be interesting to go back to the drawing board and see what kind of interaction can we prescribe that will be a bit more complicated, but still can be made in the lab, and we can see S and P wave pairing in cold atoms. Another thing to look at would be spin polarization. For example, imagine a system that is fully polarized, 10 spin-up particles. Those clearly will have a ground state of a purely P wave superfluid. On the opposite side, a fully unpolarized system, I'm just showing you here that it has a ground state of pure S-wave pairing. Between those two extremes, there should be a tipping point. Now, that tipping point is very interesting to see what would happen. Is it a sharp transition? Would that S and P wave state be more favorable at this transition point? That's actually something that will be interesting to see. So these are still ongoing investigations, so stay tuned for those. But I talked about S-wave pairing. I talked about S and P wave pairing in cold atoms, which we also call mixed spin pairing. So mixed spin pairing has actually been predicted in nuclei. So let me switch now to nuclei. I talked about neutral matter, cold atoms, and talk about nuclei. So what we know about nuclei? Pairing in all observed nuclei is of spin singlet, what I've been calling up to now as S-wave pairing, and also between same particles, so neutron, proton. That has always raised the question, why is that? Because we know in general that the interaction between unlike particles is stronger. So about a decade ago, an explanation was proposed on the mean field level that if I think of a particle in a mean field level where it just experiences all the particles as a frozen configuration around it, then it was demonstrated that it's actually the spin orbit field that is called by all those other particles that suppresses the two-bit pairing. And because the spin orbit field tends to be a surface effect on the surface of the nucleus, at large nuclei where a surface to bulk ratio is small, it has been predicted that triplet nuclei might be able to be found, and specifically on the region of around A + 100. Soon after that, it was predicted that on a transition from that region to the S-wave pairing, the singlet pairing that we know, on the transition between those two, there should also be mixed spin pairing. Now, if we were able to observe any of those types of pairing, triplet or mixed spin pairing, that would be a very interesting, that would be a very interesting observation because it would be novel nuclear pairing that we've never seen before, and we actually we can see it in experiments. It has, of course, we see enhanced neutron transfer reaction cross sections. And also been theorized that in the existence of any type of spin triplet pairing, be it within mixed spin pairing or spin triplet purely, would generate similarity between the spectra of odd and even nuclei. Now, that was, let me just actually show exactly the region that was predicted. So this is exactly the region that was predicted, where here we're changing the color coding a little bit. We have green for the singlet, blue for the mixed spin, and red for the triplet. However, this is a region that we know that it has non-negligible deformation. Now, deformation is known to reduce pairing because it reduces the single particle level density at half filling. That's something known that we know that for a long time. However, we don't know what is the competition between triplet and singlet pairing at the presence of deformation. Which one of the two is suppressed more, and what does that mean for mixed spin pairing and spin triplet pairing, for example? To connect, so in other words, to connect these results to any type of experiment, this is a study that needs to be done. Just for context, there is an experiment that had been proposed to run a triumph to test exactly these results. It was proposed in 2019. I'm not sure what its fate right now, because it was with the pandemic, everything was delayed. Last time I checked, it was waiting for beam time. So I hasn't happened yet. But this is something that people were trying to look into. So that's exactly what we did. We made a phenomenological model to look into the competition between singlet and triplet pairing at the existence of deformation. So what is that phenomenological model? We use the HFP treatment, the HFP theory, which is just a generalization of the BCS theory. Again, we describe our system as a system of free quasi-particles. Put it in a different language. So we start with a pairing Hamiltonian, and we try to find the quasi-particles that make this Hamiltonian into a free quasi-particle Hamiltonian. And then the ground state of the system is defined as the vacuum of those quasi-particles. How does deformation come into this? Deformation comes from the single particle states. So this is a mini-field treatment. Each particle moves in a frozen configuration of all the other particles, which that frozen configuration follows the density profile of the nucleus. So for a deformed nucleus, that means that we have a deformed potential, and also a deformed spin orbit term as well. There's a lot of ways to model deformation in this sense. We choose a safe way. We go with Cassini ovals, which have been used in the past to model deformation, even at extreme cases of fission and so on. We can generate any type of deformation with Cassini ovals. This is just some examples I'm putting for you here. So these are ongoing investigations, but some preliminary results show that spin triplet pairing seem to survive deformation, and actually is favored compared to singlet pairing. It's favored by it. So, for example, here I'm showing you some preliminary results about for a mixed spin nucleus, which is mixed spin at zero deformation. As we increase beta 2 deformation, we see that there's a net effect of decreasing the pairing correlations that is expected, but it turns from mixed spin into a triplet nucleus at a non-negligible deformation. Again, those are ongoing investigations. Stay tuned for those. They will be published very soon. So, of course, if we find nuclei that remain spin triplet paired after deformation, that will be a very exciting result that we can actually maybe see in the lab in those experiments that have been proposed. But also, if we find some mixed spin pairing nuclei that survive deformation, it will be interesting to see what we can do with those. We can use them as data points to create density functionals, and with those we can do, for example, dynamics. For example, it has been recently shown that S-wave pairing increases the threshold for fusion. We need to see what happens with mixed spin pairing. We will also do more exotic stuff. We can look into what does the existence of mixed spin pairing mean for different nuclear matrix elements. For example, the region of A = 130 is a region where some nuclei are chosen by Snow Lab to look into double beta decay, influence double beta decay. So it'll be interesting to see what that means for these experiments as well. So to put everything into some takeaways, first about S-wave pairing, I showed you how we did a exact description of the S-wave pairing in neutron stars, in neutral matter in the inner crust of neutron stars. We did a lot of phenomenological investigations that guided an exact aggregation calculation. For SMP wave pairing, mixed spin pairing, cold atoms, we demonstrated that it seems that mixed spin pairing doesn't exist in the at least in the mean field level in the ground state of one polarized Fermi gases, but might exist at finite spinning balance, also in more exotic settings, and also for spin triplet pairing in nuclei, it seems to survive deformation and be slightly favored compared to singlet pairing. So let me just thank all the co-authors for all these papers and collaborators: Stefano Gandolfi, Joe Carlson from Los Alamos, Kevin Schmidt from Arizona, and Dean Lee and his group, Caleb Higgs and Gabriel Given, that are working with us on the cold atom stuff, and also conditional resources provided by NERSC and Sharknet. I also want to thank Ryan for driving down here, and you for your attention. Thank you very much. If you have any questions, let's discuss. Yeah, I think it's a good question.
Sorry, I didn't understand the following. If you have many pairs belong to the spin, what would be the total spin of the ground state? How they are coupled?
So, in terms of a neutral matter, for example, or in cold atoms in an extensive gas, there will be different states that are going to produce, right? For how we know it would couple, but that doesn't come into a meaningful treatment. We don't look into that.
So essentially, you need some extra interaction. If you define this interaction between polarized pairs.
Yeah. So beyond the BCF treatment, we can have interactions between pairs as well. Is that what you mean? Interactions between different pairs?
Yes. That's my question.
Yeah. So of course, after we do the meaningful treatment, which is essentially the meaningful treatment is that each pair doesn't know about the other pairs. That's what the meaningful treatment says. It's the beginning point where we can do more fun stuff afterwards. Dean and his group are working on blast calculation. All of those will be taken into account systematically, but on a meaningful level, we don't take into account any interaction between pairs. We're just looking into can we have a superfluid where the pairs don't know about each other, but they do pair in different channels.
So then there is a huge degeneracy, right?
Well, beyond the meaningful treatment, there could be, yeah.
So would the gaps that you get for the triplet pairing mass relations so that these differences or masses and something?
So actually the gaps we calculate them that way, we calculate them with odd even mass staggering. So it should affect.
So how does that was I don't know. How many people
So
they are able to
so that's a good question because like what I showed were not actually gaps, were correlation energies. So that's the energy between the superconducting, the superfluid state, and some reference state that exhibits zero pairing. Of course, after that we calculate pairing gaps, and we're in the process of doing that. And we compare them. Of course, anything below 0.5 MeV, it's other question. We don't see it.
So does it mean that to a certain parameter you have x
So
and then at some point it changes
so
from one beta two, then you only have triplets?
So that's for a specific nucleus, right? So it's specific that at zero deformation, it's mixed spin. As we increase deformation, the ground state changes from mixed spin to purely triplet.
So what's surprising the sharp transition beta two is it really a sharp transition or
Starting
something is sent to have a mix going and then that tricks it.
So how do we? So I think the question of how do we characterize this nuclei, right? So we calculate essentially the overlap. We look at the two-particle wave function. We see which part of it is singlet, which part of it is triplet. Of course, there is an arbitrary definition of what we call mixed spin, what we call triplet, and what we call singlet. So if I were to plot the part of the two-particle wave function that is singlet and triplet, it's not actually a sharp transition. It goes smoothly. You just have to put some bounds, what we call triplet, what we call singlet. Yeah.
Thanks. Welcome to second.
Thank you.
Is the mic okay? Okay, great. So hello, thank you for having us. I'm Ryan, as introduced. I'll be starting my PhD without fall, but I'm wrapping up some projects for my master's, and that's what I'll be talking about today. So broadly, we're going to test chiral EFT interactions, and we're going to test their perturbativeness using quantum Monte Carlo. So luckily, George drew the short straw, so I don't have to spend too much time on background. But we're broadly interested in the neutron matter that's found in the inner crust of neutron stars. And so to a first approximation, we think of this as pure infinite neutron matter with only S-wave interactions. And if you want to study a system like neutron matter in neutron stars, like George said, we're tasked with solving the nuclear many-body. So it's the many-body Schrodinger equation. We know that for a few simple systems, it can be solved analytically. But for anything realistic, any truly many-body calculation, we're not solving these on pedigree. It's not shocking information. So really what we need is two ingredients. The two ingredients are powerful computational approaches and an accurate description of the nuclear interaction. Now, there are a whole host of powerful computational approaches out there in the field today that can broadly be described, as George said, as phenomenological or ab initio. For this talk, I'll be focusing on quantum Monte Carlo, which is our many-body method of choice, and the second ingredient, which is that accurate description of the nuclear force. So I'll start with quantum Monte Carlo. As George talked a little bit about, it's achieved by taking the Schrodinger equation and mapping it to an imaginary time evolution. And so once we've done that, we propagate our trial wave function with the imaginary time evolution operator, and we project out the ground state energy of the system. To get a sense of how that works, we can squint at the imaginary time Schrodinger equation. If there was no potential, we just got a diffusion equation. And if there was no kinetic energy, we have a growth decay rate equation. And both of these processes are simulated by diffusion Monte Carlo. You can see that we start with walkers distributed uniformly in space. In areas of low probability, they die off. In areas of high probability, they're duplicated. And we end with walkers distributed according to the ground state of the system. And so I won't talk too much more about the tool. George talked about it in his talk. I will talk, however, in a little bit more detail about the nucleon-nucleon interaction. So often, so we all know that it's fully described by QCD, but at the energies where nuclear physics becomes interesting, those calculations are non-perturbative, they're not easy to do, and so we can't get to an ab initio study of nuclear physics starting from QCD. As a result of that, there isn't really an agreed upon form for the nuclear interaction. So often a first step would be phenomenological potentials. Back in the day, this would be something that takes advantage of the effective range expansion. So you would take a potential, you can tune its scattering length and its effective range to reproduce the low energy physics of your interaction. If you wanted to go one step in sophistication beyond that, you would use something like the Argon group's AB18 potential, where now you have an operator structure and you're fitting your phase shifts to thousands of experimental measurements in order to reproduce them and provide a better description of the nuclear force. And then you might say, well, some people might say, isn't that good enough? Like if you're using all these phase shifts, surely that's a good enough description. More recently, we have these potentials from Chiral EFT. They represent an improvement over the previous operator potentials in a variety of ways. They respect the underlying symmetries of QCD, and they do that by expanding their expansion in low momenta and by employing something called power count. So I've just got power counting on the right, right. And this is still sort of an open question on what the right power counting is to use. For everything we're going to talk about today, it's just Weinberg power counting, but I'll come back to that a little bit at the end. One of the other ways that it really represents an improvement over something like an Argon AB18 is that the many-body forces emerge naturally through the power counting process. You don't have to add in the three-body forces, they come out naturally as you create it. And so in sort of the last 10 years, there's now local forms of these potentials that can be used in quantum Monte Carlo. And similar to the momentum space versions, they have leading order terms, next to leading order terms, next to leading order terms. And I'll come back to this in a little bit, but we're really going to check that, are they perturbative? Is it really a perturbative expansion? Before I get into that, it's not a widely studied problem, how perturbative they are, and especially in a quantum Monte Carlo context, and I'll try and explain why it's a difficult problem to deal with. So just coming back to first year quantum mechanics, we have the first and second order correction for a perturbing potential. And so we know the first order correction can be calculated easily, QMC, but the second order correction presents a little bit of a problem. If you remember, I said that DMC projects out the ground state energy of our system. And so we don't have access to these higher order energy states, and we don't have access to the higher order wave functions. So we need some way around this. We need some way to kind of sneak around this. So before I describe our contribution, I'll just do a brief kind of recap of the state of the field. So there have been, luckily the deuteron is a relatively simple system, it can be solved analytically. So there have been deuteron calculations for a variety of potential cutoffs, which is a measure of how hard or soft the potential is. And we can see a trend starting to emerge here. We see it as they go to harder cutoffs, the speed of the convergence slows down. They're not necessarily agreeing with the non-perturbative results. There have also been very recent paper by Dean Lee and collaborators, where they developed a method by using lattice QMC to calculate the second-order perturbation theory, so the second-order perturbation result. They explore a variety of light nuclei for a single measure cutoff, and they're finding very good agreement between their non-perturbative and perturbative results. There have also been some continuum QMC calculations, only the first order, where they looked at a variety of cutoffs, and again, we sort of start to see that trend that as the potential gets harder, that the convergence slows down a little bit. So now that we've set the stage, I'll talk a little bit more about what our project was trying to solve and what we did. So essentially, we wanted to develop a method that could be used for few body systems and many body systems. We wanted to use a non-perturbative technique like quantum Monte Carlo in order to treat the interactions perturbatively, and we wanted to easily be able to handle a variety of different momentum space cutoffs. So I'll start with this. It may not look like much at first, but if you kind of bear with me for 2 slides of math, I hope I can convince you that it is something worth looking at. So we'll start by introducing a resolution of the identity and splitting the sum into k equals 0 and k greater than 0. You might wonder why we're doing something like that. But already this first k equals 0 term looks an awful lot like the first order correction. So now we just need to do something with this second term. Okay, so we will then, so now that we've inserted our identity, we've split the sum, we'll carry out those integrals, and now this second term starts to look an awful lot like the second order correction. Luckily, if we project a very large imaginary time, this exponential dies off, and we can recover both the first and second order correction from an imaginary time propagation with no sum calculation involved. So hopefully I've convinced you, at least squintingly, we can get the first and second order correction, and I'll talk a little bit about our results. Oh, sorry, I will first practically talk about how we actually do the calculation. So what we do is we take that original term and we calculate the integrand in DMC, so throughout the imaginary time evolution, and then we fit its behavior based on an intermediate step in the calculation, and from that you can extract both the first and second. So after benchmarking for some two-body systems that you can do analytically, we started looking at some nuclear physics inspired systems. So this is 2, 4, and 6 neutrons in a harmonic trap. We used a phenomenological potential, and we perturbed from the neutron-neutron interaction to a neutron-proton. And so it's not a lot to look at on the left, but if we subtract off the 0th order energy and don't show it, you can see that our first order results aren't enough to recover the non-perturbative neutron-proton energies. You need to include the second order correction in order to recover the non-perturbative results, which sort of follows the earlier trend and will continue as we go. So then we come to our main project, which we wanted to test the perturbativeness of these chiral EFT interactions. So what we did, we took 66 neutrons in a periodic box, which has already been shown to be a very good approximation of the thermodynamic limit. Our perturbation moves us from an NLO interaction to an N2LO interaction, and we're going to do this for 3 values of the coordinate space. So I'll start with the softest interaction. Here, unlike or similar to the neutron-proton case, we see that our second order corrections agree very well with the non-perturbative results. And the first order corrections, not at all, but the second order correction brings us back down to the non-perturbative N2LO energies. If we move to a slightly more intermediate interaction, we see that at low densities, there's good agreement between the non-perturbative and perturbative results. But if you look at the right-hand side of the plot, you can see that DMC doesn't do a great job in the high density regime. And this is because you start to include more than just the S-wave interactions. But like I said, low density, we're still getting very good agreement. So perhaps then the most interesting place is the hardest core potential we have. And here we see that the second order correction doesn't, at essentially no densities does it agree with the non-perturbative results. And so we're interpreting this as casting some serious doubt on how perturbative the potentials are when they have harder cores. it at least shows that you need at least third order corrections in order to recover the non-perturbative results. And so then just to recap everything we found there, so it's easier to perturb from NLO to N2LO with softer potentials. At the two softer potentials, we have very good agreement between non-perturbative and perturbative interaction results. And then you need higher order corrections for the hardcore potentials. And maybe there's some doubt as to how perturbative they really are. I'll talk a little bit about kind of the next steps in the project. Something, if you're familiar with QMC at all, any non-local operator, so something that depends on the velocity of your particles instead of their relative position, can't be treated, has to be treated perturbatively in quantum Monte Carlo. So it seems like a natural merging, natural next step for the project to start looking at these non-local operators. And there are also new maximally local versions of the N3LO potentials that have terms that they have to be treated perturbatively. So you have to treat them perturbatively in QMC, so it would be nice if you could get the second order correction. So we're working on that now, and hopefully we'll have results soon. And I've also included, it would be nice to look at perturbations between something like the pion-less EFT versus what we're talking about here, which is pion-full EFT. If you could show that one was more perturbative than the other, that would be an interesting result. And it is possible, like there is also the possibility of looking at third order corrections. You can see it's obviously a little more complicated, but in practice it should be possible. And I will then summarize. So we've developed a new method for calculating a second order perturbation theory in QMC. We've tested the perturbativeness of modern chiral EFT potentials. We found that hardcore potentials need third order corrections are higher, and maybe we've cast some doubt on how perturbative these potentials really are. And then, as I said a slide ago, there are some exciting opportunities to keep probing nuclear many-body physics with this. And with that, I will thank you and my co-authors and welcome any questions.
So this convergence, so normally you try to evolve the system to imaginary time and to switch the interaction completely, that the system has a lot of reorganization. But if you apply phenomenological, like previous talk, some Hamiltonian, that's from which you switch to the microscopically based, then and the wave function is less rearrangement, then you have faster convergence and perturbative terms are smaller. And, you sort of talk in generalities about the interaction, so I don't know what you do and what you pursue.
Sure. So I think I understand what you're asking. You're right that maybe you can configure things to be easier to handle with phenomenological potentials, but the whole idea behind the chiral EFT interactions, there's supposed to be a perturbative expansion. So it should be perturbative to go from LO to NLO, NLO to N2. I don't know if that's what you're asking.
Well, okay, let's say you have a finite system and as your starting interaction, the system doesn't bounce, it falls apart.
Okay.
We switch on the interaction, it's supposed to suck itself in and make it self-consistent. So, that will take forever, never ever see it solved. So you try to help the system and put it onto the right track so that the rearrangements that it does are really small, not try to tag them on them.
Sure. Yeah, I don't know. I don't know that I have an answer for you.
Okay.
Maybe we can talk a little bit after. I don't know, but yeah.
Okay. Questions? Yeah.
So if I'm working in Java, it's kind of like effectively here, and you can calculate this. So the question is like, that's all that possibly cool. Like you have a ground state focus method, but it knows something 100%. Yeah. The question is like, can you do that in something?
So you can calculate excited states in QMC. It's just if you remember, George, you mentioned that you want your trial state to be non-orthogonal to the ground state. So if you were to use a trial state that was orthogonal to the ground state, you'd be able to calculate something like the first excited state, second excited state. So there has been some work by Bob Rowinga. They've looked at the first few excited states.
Questions? Yeah.
So, what is that's Bob? So, action, the low energy component phase, we use the same conditions of the big.
For the LECs between NLO and TOLO? No, they're different. Yeah, so the so they're fit separately, and then the perturbation is just you take nu and TOLO and subtract off the old. They have different.
Prospects. So you want to kind of motivation. So in this case, what is the argument to say that the non-mechanical part of the separator is
It's not necessarily that it necessarily be perturbated, but it has to be. So
okay, so you hope that some of them because then you reach
for N2O, the spin orbit term is already treated. And then and now these doing like a 3 or 4 terms. So yes, if you felt like sort of the to-do list, we just really wanted to start with. That's why we could have started with AFDMC and nuclei, but we wanted to start with simple DMC neutron matter, test it where it was easiest to test, and then build it.
So one other trick you can try doing is doing a shift of your NLO, putting a little piece that you can do non-perturbatively from N2O into your NLO, like putting around the LECs, readjusting that to make the perturbation converge faster. Because you're going to the same place, you just add here and subtract there. But the thing is, he's trying to reproduce non-perturbative compounding results anyways. Perturbation theory was just a tool to get there. So the endpoint's the same. Any other questions? No, let's thank Ryan and George both.